Has there ever been life on Mars? It's a question that has challenged scientists since the 1890s. The eccentric and wealthy Percival Lowell pointed his powerful telescopes at the red planet and claimed to see man-made canals. A flood of alien fantasy followed and persisted into the 1970s. The Viking 1 and 2 spacecrafts landed on Mars in the late 60s and early 70s in pursuit of evidence that life had once existed here. Viking images provided the first glimpses of what looked like riverbanks. Tall mountains loomed higher than Everest on a planet a third the size of Earth, and polar ice caps locked up oceans of water. But Viking's probes proved only that Mars is a cold world ravaged by violent dust storms. Questions remained. Did the spacecrafts miss vital clues to a past some 4 billion years old? Did life gain a foothold when the planet was warmer and wet? Since the Viking mission, scientists have learned that the most primitive of life forms on Earth thrive in boiling hot springs. Photographs suggest that hot springs like these in Yellowstone National Park were once common on Mars, and Martian meteorites contain minerals typically found near hot springs on Earth. A new era of Mars exploration is about to begin, and scientists like NASA paleontologist Jack Farmer can't wait.
Here on the edge of this hot spring, we have a place where microorganisms, bacteria, are being turned to fossils before our very eyes, the kind of fossils we'd like to look for on Mars. The waters are also loaded with dissolved minerals, and as the water cools, particularly in shallow areas, the minerals come out of solution and coat the organisms and entomb them while they're still alive, producing sort of mummies, if you will. We need to go back to Mars, and we need to look for these kinds of places, because these are the environments where that fossil record is likely to be preserved, and this will help us answer the question about life on Mars.
The search for signs of life on other worlds grows more scientifically sophisticated each year. And still, evidence persists that we just may find it on Mars. An answer to one of astronomy's most insistent questions may be just around the corner. They begin in clouds of dust and gas so far away, we would need 100,000 years to reach them. Gravity gathers hydrogen gas and particles of dust, and the clouds grow more dense. Squeezed tighter, the hydrogen heats up to a fantastic 18 million degrees Fahrenheit. Nuclear fusion turns hydrogen into helium, and the fire ignites. A star is born. Astronomer Michael Shara compares a star's life cycle to our own.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act, because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart.
Of course, a star may live for billions of years, and stellar age has nothing to do with lifestyle or heredity. It's all about size. Smaller stars burn cool and dim. When their fuel burns out, they just fade away. A medium star, like our Sun, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core harder, the star grows hotter and the outer layers puff up, engulfing nearby planets in its fiery demise. Finally, the outer layers blow off into space, and a dense solid core remains. This white dwarf is a dying star. A bigger star, say twice the weight of our sun, lives hot and dies young. It burns through its fuel in just millions of years, and it doesn't go quietly. There's more material here for gravity to constrict. The star goes out with a bang called a supernova. Gravity packs the remains into material far denser than white dwarfs, called neutron stars. A teaspoonful of this stardust weighs more than a cruise ship packed with people. Some enormous stars gone supernova become so dense they turn into black holes. Think about it. A massive explosion leaves gravity unchecked, and matter is squeezed into something unseeable, stretching as far as miles and weighing incomprehensible amounts. Got it? Invisible but deadly, pulling in matter all around it. Even light can't escape. Not to worry. Supernovas are rare. A galaxy like ours, of 100 million stars, may experience only one exploding star in a century. They begin in clouds of dust and gas so far away, we would need 100,000 years to reach them. Gravity gathers hydrogen gas and particles of dust, and the clouds grow more dense. Squeezed tighter, the hydrogen heats up to a fantastic 18 million degrees Fahrenheit. Nuclear fusion turns hydrogen into helium, and the fire ignites. A star is born. Astronomer Michael Shara compares a star's life cycle to our own.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act, because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart.
Of course, a star may live for billions of years, and stellar age has nothing to do with lifestyle or heredity. It's all about size. Smaller stars burn cool and dim. When their fuel burns out, they just fade away. A medium star, like our sun, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core harder, the star grows hotter and the outer layers puff up, engulfing nearby planets in its fiery demise. Finally, the outer layers blow off into space and a dense solid core remains. This white dwarf is a dying star. A bigger star, say twice the weight of our sun, lives hot and dies young. It burns through its fuel in just millions of years, and it doesn't go quietly. There's more material here for gravity to constrict. The star goes out with a bang called a supernova. Gravity packs the remains into material far denser than white dwarfs, called neutron stars. A teaspoonful of this stardust weighs more than a cruise ship packed with people. Some enormous stars gone supernova become so dense they turn into black holes. Think about it. A massive explosion leaves gravity unchecked, and matter is squeezed into something unseeable, stretching as far as miles and weighing incomprehensible amounts. Got it? Invisible but deadly, pulling in matter all around it. Even light can't escape. Not to worry. Supernovas are rare. A galaxy like ours, of 100 million stars, may experience only one exploding star in a century.
Engines throttling up, 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up. 1 minute, 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
This is the passageway that the astronauts would have used. You see it retreating there on the left. This is the passageway the astronauts would use in order to get out of the spacecraft in the event anything had happened up to this time. Now, of course, the only way they can get out in the event of some difficulty is to eject, which they can do even at this point. And that would be the least desirable way for them to abort the mission in any way, because, of course, it would be extremely dangerous. Extremely dangerous. Well, 4 minutes and 27 seconds to go before liftoff, before the start of this historic mission. A mission that has never been flown before. They've never used the solid rocket boosters. They never before have sent a spacecraft into orbit that is going to come down as a plane, landing essentially as a glider, a powerless glider. Look at those huge engines getting ready to receive now the millions and millions of pounds of thrust that will catapult this spacecraft and this really strange assemblage off the Earth. We're going to go to Lynn Scher, who is down at the VIP section now, to tell you a little bit more about what to listen for, some of the acronyms that will be used as the launch proceeds. Lynn?
Yes, Frank, I am here at the VIP Center and right in the shadow of the VAB. That means I'm with some very important people in the shadow of the Vehicle Assembly Building. And it's easy to use these acronyms around here because sometimes it seems as if NASA is just one giant acronym. For example, here are some of the terms that everyone is going to be hearing in just a few minutes. First of all, there is SRB-SEP, and that's when the two solid rocket boosters will fall away. And then you'll hear MECO, which is main engine cutoff, just over 8 minutes into the flight. And then there's ET-SEP, when the external tank, emptied of its liquid fuel, is jettisoned. Two acronyms no one here wants to use or wants anyone to hear. RTLS, which is return to launch site, the most dangerous forced landing right here back at Kennedy Space Center. And AOA, abort once around. That's a forced landing after only one orbit around the Earth. But I must tell you, Frank, no one here at the VIP Center is saying anything in acronyms right now. All they're thinking about is the word liftoff. They started to cheer when the clock began again at 9 minutes. Everybody here anxiously hoping, waiting, watching. Back to you, Frank.
The President's message that Jules mentioned a moment ago said, in part, you go forward this morning on a daring enterprise and you carry the hopes and prayers of all Americans with you. And astronaut John Young, the commander of the mission, replied, that's a right fine speech. We sure appreciate it. All right, we have 2 minutes and 17, 16, 15 seconds to go to launch. Jules and Gene?
That's it, Frank.
Looks good, huh?
That's the commitment to go.
Yeah.
The White Room is back. The APUs, or auxiliary power units, have started, which power the flight surfaces and controls. And unless something catastrophic goes wrong, it's a go. By the way, everything happening now is being done automatically by computers. They can be overridden, but so many thousands of things are happening all at once, Gene.
Well, it's all in the computer checkout. There's too many things for any one man or team of men to do. We're monitoring effectively in the control center the computers themselves, who are in turn monitoring all the systems of the boosters in the spacecraft. I might add that the President's message was a very moving message, and believe me, at this point in time, I can testify by my own personal experience. A prayer now and then helps, because you need all the help you can get on one of these missions.
It's emotional but precise.
Well, there are plenty of prayers being said right now.
Well, and I'll tell you, I'm getting a few butterflies myself right now.
No matter how many times you watch these things go, boy, you've got to realize what it means.
Every time's the first time, whether you've been there before or not. And Godspeed with John and Crip. That's going to be a great one.
Godspeed indeed.
Will be armed just a couple seconds from now. It has been armed. T-minus 45 seconds and counting.
That's a blast of cooling water, Frank. That protects the heat tiles from the blast of the solid rocket engines.
T-minus 35 seconds.
To shield them so they're not knocked
away
off.
from switching to the redundant sense sequencer. T-minus 27 seconds. We have gone for redundant set sequencer start. T-minus 20 seconds and counting. T-minus 15, 14, 13, T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start.
Come on, baby. Come on, baby. Go! Oh, honey, go. Fly like an eagle. Go. Unbelievable, Jules. You guys are gone. They've rolled now, Jules, and they're on their back. They're going to pitch over on their back. Roll for those islands. They're rolled over.
Just arcing straight up into the sky. What an unbelievable sight. I didn't think anything could match an Apollo.
Roger.
Look at that thing go.
The trail of fumes you see is from those solid rocket boosters. Which are going to come on.
Houston, you're going throttle up. Roger, go throttle up.
About a minute.
They're through the maximum aerodynamic pressure now to get back to 100%.
They've actually throttled back a little bit to get through the maximum pressure on the vehicle, and now they've gone back to full throttle. And everything looks to be perfectly perfect, perfectly normal American thunder in the skies.
Roger, Columbia on a nice ride. You're lofting a little bit, so you'll probably be slightly high in staging. 1 minute 45 seconds coming up on go, no, go. Columbia, you're negative C.
Okay, there.
That call up says that Columbia, the altitude is too high for ejection seat use. Columbia, your go for SRB step.
All right, they're cleared to get rid of the SRBs.
2 minutes 4 seconds, standing by for SRB step confirmation.
And too high to use ejection seats, but not even needing them. There it is.
Roger on the step, Columbia.
See with the full.
Hallelujah, baby.
Mark, 2 minutes 20 seconds, confirm solid rocket booster step.
Both of them are gone.
And now they'll come down.
Mark, 2 minutes 30
In the
seconds.
Atlantic.
On-board guidance is converging as programmed. Columbia is now steering for its precise window in space for main engine cutoff.
They're at an altitude of over 30 miles
Columbia
now.
now 39 nautical miles in altitude, 42 nautical miles downrange. Mark, 2 minutes 50 seconds. Columbia, you're looking a little hot. All your calls will be a little early. Columbia
All right.
now has 2-engine
It'll be hot.
A little faster than I thought.
Roger. 3 minutes. Young and Cripp and Rayleigh moving out. Now velocity now reading 6,200 feet per second.
And that's over 5,000 miles an hour already, Jules.
Mark, 3 minutes 15 seconds. Columbia now 51 nautical miles in altitude, 66 nautical miles downrange. Velocity now reading 6,500 feet per second. Mark, 3 minutes 30 seconds. Columbia now 55 nautical miles in altitude, 78 nautical miles downrange. Mark, 3 minutes 40 seconds. Standing by for a return status check and mission control by Flight Director Neil Hutchinson. Columbia given a green to continue.
Everything fine so far. The solid rocket boosters have fallen off.
3 minutes 55 seconds. Standing by for Press D'Amico, which says Columbia should lose 1 engine. Press stand by, Press D'Amico. Columbia continues flying forward, coming up on negative return.
30 seconds, and if they'll be on their way.
Mark, 4 minutes 8. Columbia stand by for negative return. Mark, negative return.
They're not coming back here.
Woo. Here is a view from a chase plane, one of the several chase planes that have been sent out to help track Columbia as it goes.
Start, 2, 1, 0, and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Ignition, Fred.
Roger. Clock start, flight. Roger. Press is go, all engines. Roger.
Looks good here, flight. Good agreement.
Okay, boost ahead, Eva.
I'm going to try to get on the bottom bolt now.
We had a good aliveness test.
Oh, good. All right. Outstanding. It's hot for me because the arms are stretched. Okay. How about a little bit of support? Like 6 inches. I can give you a port.
Magnetic fields affect the hot gas in the Sun's chromosphere, an inner layer of its atmosphere. The fields make loops of gas rise up and break apart, creating bright prominences and dark filaments. Solar quakes also occur in the chromosphere. When magnetic loops break apart, they release radiation and tiny particles that may interfere with electronic instruments. Our Sun is constantly rotating and changing. The Sun's outer layer, the corona, features events such as massive ejections of particles and energy, and disturbances called Morton waves, which ripple over the Sun's entire surface. In this view, an instrument blocks the body of the Sun so cameras can record the corona without interference from the Sun's bright disk. Sometimes comets crash into the Sun, disturbing it enough to cause explosive events in the corona.
Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
I'm going to step off the limb now. That's one small step for man. One giant leap for mankind. Beautiful view. Isn't that something? Magnificent sight out here. Magnificent desolation.
Space Lab, a laboratory carried in the Space Shuttle's cargo bay, provided a place for astronauts to perform scientific experiments. They carried out studies on the effects of weightlessness, on humans, on animals and plants, on chemical reactions, and on materials that might be used to build structures in space.
Oh, this is going to be some kind of different ride. Well, Tony, that's your house rock right there. Very good. Down to about 3 centimeters. I was in bag 569. Hippity hoppity, hippity hoppity, hippity hopping over hill and dale.
Ever wonder why stars are so bright, or how the Sun produces so much heat and light? It turns out each star is a giant nuclear furnace that releases energy at its core. It's nuclear energy that lights up the sky. The Sun is the star that glows closest to the Earth. It gets its energy by burning gases at its core in a process called fusion. Like most stars, the Sun consists almost entirely of 2 gases, hydrogen and helium. During fusion, hydrogen atoms collide with such strong force that they fuse together to make helium. Each second, 600 million tons of hydrogen convert into 596 million tons of helium. The missing 4 million tons of matter are transformed into energy. This process is only possible because of the enormous heat and pressure found at the center of the Sun. It's about 25 million degrees Fahrenheit in there. Energy moves from the center to the surface of the Sun with dramatic results. The most spectacular sight is an enormous explosion of energy known as a solar flare. These flares send radioactive particles into space, particles that get carried by solar winds. They reach the Earth in a day or two, where they're deflected by the Earth's magnetic field. But at the North and South poles, these particles can hit the Earth's atmosphere and produce brilliant light shows known as auroras. While not everyone has a chance to see an aurora, all of us certainly experience the sun's energy each day. At 93 million miles away, we are far enough removed from this star to enjoy the benefits of its heat and light. During photosynthesis, plants collect energy from the sun's light and use it to make food. Like every star, someday the sun will run out of the gases that fuel it and gradually fade away. Astronomers believe the sun is more than 4 billion years old and has already burnt up about half of the hydrogen at its core. But no need to worry. It still has about 5 billion more years to go. The nuclear energy that powers every star seems almost inexhaustible, and for that reason, scientists would like to find a way to generate it on Earth. But that's a tall order. It requires them to duplicate and control the same conditions found at the center of the sun. Scientists are working on ways to do just that.